faithfully delivering value and exploring great books worldwide.
Hi, this is Sally from the Book Talk Show. Today, we're diving into Furry Logic.
The subtitle is Physics in Animal Life. Most of us have studied biology and physics, but animal physics? That's rare. Actually, animals are matter too, so they follow basic physics and use it to boost survival. Even without studying physics, they use physical laws like prose, that's fairy logic. This book offers a fresh view on animals and uncovers their amazing physical tech. One author is Martin Durrani, a Brit who edits Physics World magazine. With a PhD in polymer physics, he did postdoc at Cambridge and loves explaining physics through stories. Super engaging. Co-author Liz Kalager is a UK science writer with a materials science PhD, focusing on animals through that lens. Together, they're a dream team, fun and insightful. They ask cool questions like, do mosquitoes pop their guts while feeding? How do geckos cling to walls? Cats, how they lap water? And more.
They think physics can solve what biology can't.
6 chapters cover physics topics: heat, mechanics, fluids, sound, electromagnetism, and light. Animals specialize in various physical skills, each a master in their field. First up, the heat masters. Think viral videos of blood-sucking mosquitoes. Some mosquitoes go too hard and pop their guts. The blood spills out, like all that work for nothing. We mock their greed but misunderstand. Mosquitoes aren't that dumb to burst. They're using heat physics to stay safe and suck better. How's that work?
Nobody likes free blood loss. We swat mosquitoes on sight.
So sucking blood is super risky. Males get it. They don't mess with us. But females need nutrients for babies, so they take the risk. When they find a good blood donor, they first use their needle-like mouthparts to probe the skin, pierce it, inject anticoagulant to prevent clotting, and then enjoy fresh blood. Mosquitoes know this makes them vulnerable to human retaliation, so they often act at night to avoid waking the donor. Still, they have to act fast to prevent the victim from waking up suddenly. Their strategy is to suck blood as fast as possible once they pierce the skin, then flee the scene quickly. Like a starving person sneaking into a buffet, they gorge themselves quickly and then dash away. That's how mosquitoes operate. They suck large amounts of human blood instantly, tripling their weight in no time. Sucking so much blood so fast feels great momentarily but causes an unexpected problem. Mosquitoes are cold-blooded animals with their most comfortable temperature around 25 degrees Celsius. But humans are warm-blooded with body temperatures up to 37 degrees Celsius or higher. So, mosquitoes suck large amounts in a short time.
Human blood is like humans gulping down hot pot soup. Drinking over 100 kilograms quickly would scald them.
The hot human blood causes mosquitoes to overheat, losing their ability to reproduce. Worse still, a blood-filled mosquito is like a drunkard, clumsy and slow, becoming a target for others.
They swarm over it, treating the blood-filled mosquito as a free hot drink, sucking dry all the stolen blood.
To avoid this tragedy, mosquitoes must prevent overheating, but sucking slowly would lead to a worse fate. The solution is to expel some blood and urine, carrying away heat to cool down. Research shows this trick is very effective. With each drop of fluid expelled, a mosquito's body temperature can drop 3 degrees Celsius. When it finishes sucking blood and pulls out its mouth parts, its temperature drops to match the environment, hardly hindering movement. So, next time you see a mosquito bleeding, don't be alarmed. They're not bursting their bellies, but using thermodynamics to cool down. There are many heat masters like mosquitoes.
For example, when dogs get wet, they shake violently like a washing machine to dry their fur quickly, preventing heat loss from evaporation.
Japanese honeybees use thermal weapons against invaders. They form a dense bee ball around invading hornets, using heat from their flight muscles to literally bake them alive. Beyond thermal physics, animals are also masters of mechanical principles. Next are the mechanics masters. Many animals understand mechanics, but geckos are most astonishing. They walk freely on ceilings and dash across glass surfaces. They seem completely unaffected by gravity. Consider this: An average gecko weighs about 100 grams, roughly 2 eggs. Just try sticking eggs to your ceiling to appreciate how incredible geckos are. So, how do they stick to walls without falling?
Turns out they use a fascinating force called van der Waals force.
Discovered by Dutch physicist van der Waals, it's the weak attraction between molecules caused by temporary electric fields from orbiting electrons. Van der Waals force is like miniature gravity everywhere, individually weak, but collectively powerful when countless forces combine. Like when interleaving pages of two thick books makes them hard to separate. That's van der Waals force in action.
Geckos stick using van der Waals force, but it only works within 10 nanometers. So, they maximize contact area. More surface equals stronger adhesion.
Their feet evolved complex pads with layered folds like tire treads, covered in microscopic setae that split into spatula-tipped branches for maximum surface contact. Through millions of setae, geckos amplify van der Waals forces enough to defy gravity. Now, the gecko faces another challenge. Since it can stick to walls like a New Year couplet on a door, the stronger the adhesion, the harder it is to peel off. So how can the gecko move quickly? Turns out, to avoid becoming a wall-mounted specimen, they must resolve this contradiction. The gecko's toe structure is super flexible. It can bend and contract bit by bit, just like we curl a finger, gradually peeling off the wall. Each time, the area it peels off is small, so it doesn't take much effort. When all toes are lifted, the gecko can leave the wall. The whole process is so fast that it's hard for us to catch a gecko walking on walls, allowing it to snag insects ahead. By mastering the van der Waals force, the gecko becomes a true mechanics master. Besides geckos, mosquitoes are also mechanics experts. During rain, the impact on them is huge, like a person hit by a 5-ton truck.
To avoid being killed by raindrops, mosquitoes learn to leverage the force.
Whenever hit by a raindrop, it flies with the direction, dodging direct impact and hitching a ride on the raindrop express. The third expert to appear is the cat, a master in fluid dynamics. People often say cats are liquid, but that's not literally true. Cats' achievements in fluid dynamics aren't about flexibility, but about their drinking skills. Water is a classic fluid. Inside, each molecule bonds with others, forming internal cohesion called water's cohesive force. Water can stick paper to a table. That's cohesive force at work. At the water surface, it's different. With no molecules above, surface ones are pulled by those below, creating tension. This is surface tension. A leaf floating without sinking is held up by surface tension. You can slowly place an embroidery needle on water to witness the miracle of surface tension. All animals depend on water. They must learn to use its cohesive force and surface tension. And cats excel here. Many cat owners don't realize that cat drinking is a fascinating biological puzzle. Cows drinking is easy to understand. They just dunk their mouths in and suck up water. But cats hover above the surface, lapping water with their tongues, which seems much less efficient. So why don't cats just dunk and suck like cows? It relates to water's fluid dynamics and cats' living habits. The biggest difference isn't size, but diet. Cats are carnivores, cows herbivores. Different diets mean different mouth structures. Herbivores just nibble grass slowly and chew thoroughly. No special mouth requirements. Smaller lip gaps create tight seals. Like straws, they suck water efficiently. Carnivores need wide bites to tear prey. Thus, carnivores have larger lip gaps that leak air when sucking. That's why cats can't suck. They must lap. But for ages, people only knew cats lapped without understanding how. Their movements were too fast to see details. People assumed cats curled tongues into spoons to scoop water. High-speed cameras revealed they touch water with spoon back, lift rapidly using cohesion to pull a continuous column. Before gravity breaks the column, jaws snap shut to capture water. Limited water per lap forces rapid repetition, 3 to 4 times per second. Without cohesion, thirst quenching would be harder. Underwater animals constantly experience cohesion, often as interference. Like seahorses creating turbulence during hunts, cohesion alerts prey. To avoid this, seahorses evolved pointed heads to minimize turbulence and stealthily approach prey. Besides cohesive force, some animals also use water's surface tension. Water striders are surface tension experts, also called water spiders. They can glide fast on water. Because they're super light, standing on water is like being on a trampoline, so they don't sink to the bottom.
Oh, thanks to surface tension, the water surface becomes a playground for small animals like water striders.
The fourth to appear are acoustic experts. Animals need sharp ears to sense sound, but not all use ears, like elephants, who have unique acoustic tricks to pick up extra sound info. In July 2013, at a national park in Namibia, a baby elephant got separated from its family in chaos, looking lonely and tense.
The baby elephant ran around everywhere, trying to find its mom.
Strangely, while rushing around, the baby elephant would occasionally stop and lift one front leg or one back leg, then stay totally still. It seemed like a weird ritual. At first, zoologists were just curious and didn't dig into the mystery until they saw adult elephants doing the same thing and consciously teaching the leg lifting skill to calves. Please, please. Only then did everyone realize that elephants lift a leg like a statue. Staying still in place isn't about any ritual. It's about listening for distant seismic waves. Elephants are huge, and their roars are just as loud. Normally, elephants catch these calls with their big ears, but sound waves don't travel far in air, limiting their long-distance chat abilities. But zoologists found elephant calls also include infrasound, which hits the ground and travels through it, creating seismic waves. Elephants can't set seismic waves with their ears, but they can with their feet. Their feet have thick fatty tissue full of piscinian corpuscles, which are specialized organs for sensing faint pressure signals. And
The piscinian corpuscles send seismic wave signals through nerves to the brain, so elephants can hear distant infrasound.
so why do elephants sense seismic waves? Because elephants are massive with heavy footsteps, giving them a signature stomping sound. The seismic waves they make while walking are way different from other animals, so they work as an effective communication tool. Moreover, seismic waves travel longer distances and avoid interference like wind noise, making them uniquely valuable compared to other sound waves. Elephants can gather lots of info from seismic waves, like telling if it's an elephant or antelope, their numbers and walking speed, or if a lion's nearby, so they can react in time. And so, why do elephants lift one foot when sensing seismic waves? Wouldn't it be better to feel the seismic waves with all 4 feet at once? Some scholars think elephants lift one foot while listening to seismic waves to evenly distribute weight on the other 3 feet, making them bear more pressure and be more sensitive to the waves. Plus, elephant legs are far apart, so 3 feet form a typical acute triangle. Elephants can use triangulation principles to calculate the direction and distance of seismic waves. Clearly, elephants aren't just acoustic masters, but also geometry masters. Besides them, bats are famously acoustic experts too, using ultrasound to detect insects. Insects aren't keen on being bat food, so they've learned countermeasures, growing dense hairs to sense bat ultrasound. Once spotted in a bat's range, they fold their wings and drop straight into grass, making the bat lose its target. They all use acoustics for survival. Even lobsters use sound to protect themselves. Contrary to intuition, underwater is actually a noisy place. Many aquatic animals make various sounds, just human ears can't hear them, so we wrongly think it's quiet. Lobsters are one source of underwater noise.
When they've just molted, their bodies are super soft and defenseless, so they rely on tricks to scare off predators. Their sound is like a siren, sharp enough to keep enemies away. Why? Why?
Some claim you can hear lobsters screaming when boiling them, which isn't without reason. The fifth to appear are electromagnetism experts. They use electromagnetic tech to hold an unshakable edge in the biosphere. And this time, this content came from the most important rep is bees. Bees need pollen for nutrition. But one thing baffles biologists: how bees locate flowers. Some think bees can see flowers with their eyes. But experiments show they ignore artificial fake flowers and fly straight to real ones. So flower color isn't the key factor attracting bees. Further research revealed bees actually use electric fields to locate flowers. The experiment went like this. Researchers made plastic fake flowers with sucrose solution instead of nectar, and others with quinine solution, a bitter-tasting liquid. When bees were placed among fake flowers without special treatment, they randomly sampled both sucrose and quinine, unable to distinguish them by smell.
But when researchers electrified sucrose flowers, the situation changed subtly.
Flowers with a 30-volt electric field guided bees to make correct choices. Remove the electric field and bees became blind again, meaning bees can follow electric fields to find suitable flowers and avoid bitter quinine. These are the only animals known to sense electric fields in air. Anything charged creates an electric field, flowers included. Because flowers are exposed to air, which carries many charges, especially during thunderstorms. After storms, air holds even more charges. From sky to ground, charge density varies with height, creating clear voltage differences. Voltage difference is like mountain height. Greater charge separation means higher voltage. During storms, flowers have about 30 volts difference from surrounding air, and any voltage difference creates an electric field. So every flower has a tiny electric field. But how do bees detect them? Many notice bees' fuzzy bodies. That's actually the origin of this book's title. Fine hairs are key detection tools, like human body hair standing during static. Bees feel their hair's movements too. Closer to flowers, electrostatic induction intensifies, heightening bees' perception. Then they know they're approaching a flower, not a leaf. Flat leaves can't capture enough electrons to create strong fields. Beyond sensing electric fields, bee fuzz has even greater value. When bees fly through the air, their fuzz rubs against air molecules and loses electrons, becoming positively charged, while flowers capture negative charges from the air. Pause captures negative charges. When a positively charged bee visits a negatively charged flower, static electricity pulls pollen onto its body, neutralizing the flower's charge and altering its electric field strength. Bees can sense these changes in electric field strength. When a bee detects a weakened electric field in a flower, it knows another bee already visited, saving time and boosting nectar collection efficiency. A win-win strategy. Flowers also benefit through improved pollination efficiency from bees' targeted visits. Through this unique electrical ability, bees and flowers co-evolved, securing the bee's place in the insect world. Other animals use electricity too, like electric eels stunning prey or sea turtles navigating via electromagnetic fields to their birth beaches. These amazing creatures humble us. While humans lack electromagnetic senses, our strong light perception helps us appreciate animal optical masters. Finally, the optical masters take the stage. Archerfish will showcase their specialty. Try this experiment. Fill a bowl with water. Insert a chopstick at an angle. It'll appear bent. That's light refraction creating the illusion. When light enters water at an angle, it refracts, a common optical phenomenon. We rarely notice refraction since we don't live underwater. But for Australia's archerfish, it's a real challenge. Archerfish lurk under leaves in lakes. Spotting prey like butterflies on foliage, they shoot precise water jets like bullets, reaching 10 times their body length, like spitting 20 or more meters. Biologists marvel that prey appears 35 centimeters off position underwater, enough to miss, yet archerfish still hit targets. But in fact, archerfish almost never miss. How do they pull it off?
Theoretically, the ideal shooting angle for archerfish is straight up, with no deviation, which should boost accuracy.
But archerfish ditch this best approach, not because they're worried prey might fall on their heads or hit their bodies and the water surface. If a vertical fish gets spotted by birds, it's tough to escape fast. Just like when a person's lying down, it's hard to bolt from danger. So archerfish gotta work to keep their bodies horizontal, cutting down escape time from threats. The compromise is their bodies aren't vertical or horizontal, but at a 75-degree angle to the water. Refraction's unavoidable here, yet archerfish male targets underwater. What's the secret?
After long research, zoologists found the trick lies in archerfish's unique eyes.
Their retinas are super developed. In just 1 square millimeter of key light-sensitive area, there are over 50,000 photoreceptor cells, 10 times more than other spots. Such dense photoreceptor cells gather light refracted from all directions on the water surface and cancel out refraction interference to pinpoint prey location. Once they lock onto prey, they don't budge their eyes. Instead, they adjust their body position to find the best firing angle, just like a sniper tweaking their scope. Once adjustments are done, they blast out a powerful water jet. Taking down prey in one shot, archerfish earn their rep as true optical masters. Lots of animals rock optical tech, like ants using polarized light to find home, octopuses changing color with ambient light to dodge predators. Big-eyed squid have a killer move too. They check distant plankton's glow, and if light gets messed up, wow! They bolt because it means a giant sperm whale's coming, their arch nemesis. By now, we've covered over a dozen different animals, each acing amazing feats in their physics specialties. This book's packed with content, introducing dozens of animal physics tricks. Each trick stands alone, like separate fields with walls between them, but the one thing they share is being totally mind-blowing. All right, that wraps up Furry Logic. The core message is, after reading this, you'll see animals differently. They're not just creatures but physics experts, using nature's laws to their advantage. And here's the thing. Animals and humans aren't fundamentally different. We're all low-entropy beings following physics, bridging physical and life phenomena to give us fresh cosmic perspective. Okay, that concludes our journey through Furry Logic. Reading notes are below the audio. See you next time.